welcome to the fourth electrolysis film. This is on industrial electrolysis, and in this we're going to look at how we extract aluminium from its ore and why we use electrolysis for that process, and we're going to look at what happens when we electrolyse brine, which is an aqueous solution of sodium chloride. Now you might be thinking, why do we actually electrolyse, or why do we use electrolysis to extract aluminium from its ore? Iron, for example, is extracted from its ore by reacting it with a carbon compound, or even just carbon. So in the blast furnace we use carbon monoxide to displace the iron and form carbon dioxide as a byproduct. And this process works because carbon is more reactive than iron, so displaces the iron, leaving iron on its own, and carbon takes the oxygen with it. Now that process isn't possible with aluminium. If we reacted aluminium oxide with carbon or with carbon monoxide, no reaction would occur. And that's because the carbon is less reactive than aluminium. So it is not able to displace the aluminium from the oxide. So no reaction happens. So we have to come up with another method of extracting the aluminium from its ore. And we use electrolysis. So this is what the electrolysis cell looks like. Now I have to admit that I've never actually seen one of these in action. I've seen the buildings where the cells are, huge buildings. We drove past one when I was on a trip to Iceland, and this aluminium extraction plant was gigantic. Nobody could quite share my excitement for seeing this aluminium extraction plant, but nonetheless it took a good 30 seconds for the bus to actually drive past this long building. And inside it there were lots of cells that looked a little bit like this, and you will be expected to be able to label them. And sitting in the middle of the cell here, this is where we have our aluminium ore, which is called bauxite. And I'm going to write it up here because I've not got any space down there. And bauxite contains the chemical aluminium oxide. Now, aluminium oxide has an incredibly high melting point. It's huge. And you'll hopefully remember that the electrolyte, which is going to be here, needs to be molten. It needs to be a liquid, because otherwise the ions can't move and electrolysis won't occur. So, if you're doing this process, you have a choice. Do you heat up the aluminium oxide to its ridiculously high melting point, or do you try and make a solution of the aluminium oxide? So the obvious answer is make a solution of the aluminium oxide. Sadly, aluminium oxide is actually insoluble in water, so this is much more complicated than you might first think. It won't dissolve in water, but it will dissolve in a substance called cryolite. Now, it won't dissolve in the cryolite at room temperature, and in fact the cryolite needs to be at somewhere between 1800 degrees Celsius and 2000 degrees Celsius. Now that, you might think, is a very hot temperature, and you'd be right, it is hot temperature, but it is lower than the melting point of the aluminium ore, the aluminium oxide. So actually in the long run, money is being saved by not heating it any higher than 2000 degrees Celsius. Now, inside the electrolyte, or in the electrolyte, we have aluminium ions. Aluminium has ions that are 3+ charged. And these aluminium ions are attracted to the lining of the cell. This lining of the cell is the negative electrode. Now hopefully you remember the name of the negative electrode. It's the cathode, and there's slight variation in textbooks over what this is made of, but some of them are made of graphite, so I'm going to refer to it as a graphite cathode. And the aluminium ions are attracted there because the cathode is negative. And when the aluminium gets there, the aluminium 3+ ions take electrons from the negative electrode, and they take 3 electrons and form aluminium. And so this substance at the bottom of the cell is actually the aluminium that has formed. And you can see here that there's a gap at the bottom, and when you've made enough aluminium you can just open a tap and it flows out in a river of liquid metal. Now one label we haven't completed is up here, A, and if the lining of the cell is a cathode, at the top of the cell we have our anode, and these are made from graphite as well. So here we have graphite anode. And you need to be able to label this. If you were given the blank as I started with, you need to be able to do that yourselves. Now, in the cell, if aluminium ions are attracted to the cathode, the oxide ions here are attracted to the anode. And what happens is the oxide is attracted there and forms an oxygen atom. Now oxygen atoms don't really happen. They're incredibly reactive, and 2 oxygen atoms will form next to each other and they will bond to form an oxygen molecule. And we therefore need 2 oxide ions here, and on this left hand side of the equation here we have an overall charge of 4- because we've got 2 2- charges, and that means on the right hand side we need 4 electrons there. We should probably note down which of these processes is an oxidation and which is a reduction. So reduction is the gain of electrons. Okay, so in this process we're gaining electrons, so this one is reduction. And in this process, the second reaction I've written, that's an oxidation. Why? Because it's losing electrons. Now, worryingly, we've got oxygen gas being given off from the top here around the anodes, oxygen. And this process is being done at a very high temperature, and we've got graphite anodes there. Now graphite is carbon, so we've got carbon next to oxygen at a very high temperature, and so the actual anodes react with the oxygen. Carbon plus oxygen forms CO2. So over time, this carbon on the anodes turns into CO2, carbon dioxide, and is released into the atmosphere. Now that's a little bit of an issue, okay, because the anodes wear down, they wear away. So I'm not using a black pen, but you can see that they would decrease in size. So the anodes need replacing. And that's just something you need to be aware of. It's not a major cost though, because graphite, relatively speaking, is actually quite cheap. The major cost comes from 2 things. Number 1, heating the cell up to about 2000 degrees Celsius. So the aluminium oxide will dissolve in the cryolite. The second cost is electricity. you need a huge amount of electricity to run this process. So these aluminium plants are usually built near where electricity is relatively cheap. In Iceland, there's a lot of geothermal power, and electricity is quite cheap, so it was built close to a geothermal area. There used to be an aluminium extraction plant on the island of Anglesey in North Wales, because there was a nuclear power station there. So the aluminium extraction plant was next to the nuclear power station. That would have made an amazing school trip, but is a little bit far to go from London just to see an aluminium extraction plant. So those are the two major costs. And one of the things that people put down in exams is, well, replacing the anodes regularly is a major cost. And that's not really true, because the anode is actually quite cheap. Other questions asked in exams: why use cryolite? And that's because the aluminium oxide will dissolve, and therefore the operating temperature of the cell is lower than if you were using pure aluminium oxide. Why are we using electrolysis? Okay, and that's because carbon cannot displace the aluminium, and that's because Al is more reactive I'm running out of room here than C. Okay, looks a right mess. Let's just move the page up a bit. Okay. And the final thing that quite often gets asked in association with this aluminium extraction plant is, what's aluminium used for and why is it used for these things? Well, one of the uses of aluminium is it's used to make aeroplane fuselages, and it's used for that because number one, it has a relatively low density, and another reason is it has an oxide layer that forms on top of it, and this prevents corrosion of the aluminium. It's almost like having a layer of paint over the top of the metal. So the oxide layer is unreactive and it prevents corrosion. And aluminium is also used to make food packaging, sort of containers from takeaways, drinks cans, and obviously the fact that you don't get corrosion is very important in that, because it would be dreadful if your food or your drink was reacting with the container that it was in, and so the drink or food that you bought would then be laced with various aluminium compounds. And I think that concludes this video on aluminium extraction. The next one will be on the electrolysis of brine.